Very happy to have with us today Professor Fernando Pereira from UPenn. I think most of you here probably already know him, so I don't have to say much. He has a long career at Penn, AT&T, Whiz-Bang, and other places, really sort of one of the pioneers in applying machine learning to large data related to text. And I know he really influenced me in thinking along these directions when he said, the older I get, the farther down the Chomsky hierarchy I go. and the fact that you can get a laugh out of that means that you came to the right place.
All right, so okay, so this is a talk. This talk touches a bunch of things that some of you, I'm sure, and I know some of you know quite a bit about, probably in some ways more than I do. So what I'm going to do is to cover, I mean, basically give you a little bit of what some of the main things I've been working on relatively recently, some results, relatively recent results on work I've been also doing over the last 7 years or so. My former student, Ryan McDonald, over there in New York, has done a lot, applied some similar techniques to parsing that I'm not going to talk about. You know, he's a much better person to talk about that. But so also, I mean, there's a bunch of related themes that I don't have slides for, but that kind of come out of this work or touch on this work, which are broader than just the specific technical work here. So if you have any questions, I'll have a way of going on tangents from time to time. I might not cover all the slides because of that. And if you ask questions, which I really would appreciate, you know, you can drive me into other directions as well. So this kind of think of the talk or the slides as sort of a some way of priming a conversation, if we can do that. So kind of for a long time, I've kind of been driven to work with sort of sequential problems. And whether it is doing a natural language syntax, that's an example actually from a paper with Ryan on doing dependency parsing for English. And again, I'm not going to talk about that much today. Or you know, one task that we've been working on quite actively, actually Ryan also worked on extensively when he was in my group, which is to do named entity extraction for biomedical text, PubMed abstracts. And I'll actually talk about a little bit more about the motivation for that and sort of the some of the underlying the applications that motivate that. So the point there is, you know, people have lots of biomedical texts where they like to know what is it about, what biological objects does this text discuss. We've been trying to help a number of biomedical researchers do that, as many other people have been doing. And the final example sequences that, so this is, when I came to Penn, one of the things motivated me is that I was really getting interested in application of sorts of various kinds of machine learning models for sequences to gene prediction. And now, there was computational gene prediction was alive and well, and I kind of saw what people were doing and say, oh, I think I can do better. And well, it took 4.5 years to do better. And one student was an extremely persistent guy. So it wasn't as easy as I thought it would be. I thought it would be 6 months when I started. Well, not really 6 months, but a little bit, maybe a year or so. But finally, I think we got somewhere. So now, I know we'll have a mixed audience in certain sense. I mean, some of you guys know a lot of the work I've been doing, and there's, you know, other people here who I don't know probably know less. So again, if you ask me questions, if I'm going to slowly say, hey, come on, move on, you know, we know that. Or if I'm going to, you know, if I'm going fast, just stop me. And again, let's try to make it interactive. So I'm going to use, for purposes of exposition, I'm going to use a schematic picture. And that it doesn't mean that this picture is exactly what we're doing in each application. But generally, what I'm looking for is we have sequences of some kind, whether it be text or speech. I have also worked a lot on speech, but don't have anything new to say about that. Although my former, you know, so one of the students at Penn was advised by Lawrence Saul, did some really nice work applying the techniques I'll discuss today to speech recognition. He's now a postdoc at Berkeley. Fei Shah, so he's one of the people I acknowledged in the slides. So we have sequences, and we're going to find try to identify some structure in those sequences. Now, I write those little structures as trees because it makes kind of illustration nice. But you can imagine that the structure sequence might be different kinds. So actually, let me go back in this slide here. Here, the structures in the gene case is I have a genomic sequence of some kind, and I'm going to try to label segments of it as playing particular roles. So, for instance, a gene is in a eukaryotic gene is organized in a number of different exons, which are chunks of meaningful DNA sequence that typically code for protein, although not there's some complications. I won't go into that. And then those pieces, 1, 2, 3 here, 3 exons, have gaps. There's going to be some piece of sequence here that is not part of this gene, which is called an intron. So this organization is very complex and very evolutionarily. Its role is subject to a lot of discussion still. But the end result is that whatever machinery in the cell comes along and says, oh, here's a gene I want to transcribe, and that's gated by some stuff that's up here that I don't know anything about. But there's machinery comes along and says, oh, grind, grind, grind. It's going to go along and copy this, do what's called transcription, which is copy this subsequence here. And then there's some other machine that comes along and says, oh, clip that away, clip that away. It's called splicing. And the end result is that the meaningful part of the gene in terms of protein coding is going to be these 3 pieces. And that's what the gene predictor is going to try to find in a case like this. So the analysis in this case is 3 segments, these 3 yellow segments. Separate, and the stuff here, here, and here is sort of stuff that you kind of label in a different way. So here it's intergening, meaning that is in between different genes. And here's an intron, meaning it's between the 2 exons of a given gene. So that's one structure for gene case. Here the structure might be labeled these words as part of a protein or gene name, the stuff in red, and the other words as other. I don't care. And in a case like that, the structure is some kind of graph structure. So structures can be varied depending on your application. And what I'm going to talk about applies with some caveats I'll discuss to a variety of different structural problems. So you have a sequence, you're going to map it to some structure, which I schematize as a tree just for fun. OK. So I'm going to talk about 2 main applications. One is a very old, they're both pretty old applications in this world of sequence prediction. One is named entity extraction. So where the purpose here is I have some mechanism that is going to identify mentions of entities of a type of interest, say, protein names in text, and then hopefully help us link the text to other resources that about those entities. So, and I'll give you an example of that in a moment. Gene prediction is the task I described before. Again, find the proteins, the genes that code for proteins that determine an organism's form and function. So these are tasks that people have been trying to perform for a long time and using a variety of different techniques for. And there's a syntactic analysis task that I've also worked on with Ryan, and he is the person to talk about that. And I'm sure some of you have already seen his work on that. So the technique that the kind of standard technique that people use for these information extraction problems, where the goal is to link documents and structured databases, and there are other ways of doing this. Some of which I'll allude to near the end. But the methods we are using, which in a sense are pretty traditional, where the innovation is in how we do one of these parts, is go along the text using a machine learned model to identify, to tag mentions of the entities of interest. So, for instance, protein names or person names or company names. And then once you find these mentions, you have to map them or normalize them to actually to the things that in a way that allows you to link to other external databases about these entities. So to make that more concrete, I'll give you an example that we've been working on. Many of you, I'm sure, know of PubMed. PubMed is a search engine run by the National Libraries of Medicine, which is a division of NIH. and indexes abstracts of pretty much all biomedical articles published in English. So there's a query up there that I got, and for no particular reason, except that it fits with my next example. And I'm interested in a particular condition, the genetics of a particular condition, and I get a bazillion articles, 661 that match that query. The search engine uses some ranking policy that I'm not sure about. But you can organize, you can sort by date, and so on and so forth. So it's just a standard specialized search engine. And then if you go, you can do the same in Google Scholar. You get a lot more articles. I mean, a lot of the same PubMed stuff is indexed there as well. And the ranking will be different. But this is a resource that all working biomedical researchers use every day. It has nice properties. You can download the references in a standard format that you can put in your bibliography, things of that kind. And sometimes you can get to full text articles for journals that are, open access and things of that ilk. But it only indexes the abstracts, which is what we're working on. This is an experimental system called Fable, and this has been built by the Children's Hospital of Philadelphia, which is the premier children's hospital in the country, in fact. A very well-funded place who does very innovative work in the biomedical informatics. And they've been working with us on trying to help their researchers find articles of interest in a better way. And so here's when Fable does the following. So yeah, I use the same query, but I want to find the genes that are mentioned in that query. So in the articles that talk about that query. So I'm interested in saying, I'm starting to do a study on the genetics of autism. I want to know what genes people have discussed in the context of that query. And we run the tagger that we'll developed using the techniques I'm about to discuss. And then the people at Children's Hospital developed a set of actually rule-based machinery to normalize the mentions. I mean, there's ways of using machine learning for that, which we are exploring, but they just did a baseline, which is simple, kind of doing some basic edits and so on, looking at abbreviations. And what they do is, so given the mention in the text, you map to a standard identifier, and you link to an existing database. So these are multiple places, including one you know, and a bunch of others, things like gene cards and NCBI. One of the main databases is NCBI gene, which tells you, which is a structured record about this gene that was found. It will tell things about for instance, the function. There's all sorts of information that people have put there by hand or by semi-automated means about this gene may be codes for a protein that is a kinase, say. We say how many articles mention that gene, and so on. And down here, for example, it might be that you being a researcher in this area, know the top 5 or 6 of these, but you might not realize that people had implicated this gene in this particular condition. Now, this is there's a lot to do here. For instance, are you doing any proximity kind of thing? Are you looking for those words close to the mention of the gene or not? And this system is under constant development. But this is the type of application that that motivates doing a lot of this information extraction. Is can I link articles, scientific articles, to databases that people are building independently for the same task? And this system is actually, people are really enjoying it because they were before completely unable to do this kind of query. And getting these lists, which they can then investigate. For instance, I think this is one that people were interested in because this is sort of one of the developmental genes that controls the differentiation of the sort of nervous system.
Fernando?
Yes?
Sort of backing up a bit, the way you framed the problem, one thing you didn't mention is whether you want to learn these joint sequences to structures, whether that is meant to be supervised or unsupervised or both. So in the case of information extraction, supervised seems to make more sense, whereas in parsing, it's possible you might also do unsupervised.
So actually, in both cases, you would like to do more unsupervised than we do now, right? The way it is done, which I'll describe, we have annotated. So we got a bunch of cheap biomedical graduate student help to label a bunch of abstracts with, like the way that example I had before, and they and then those basically pre-meds. Those there are plenty around Penn, and those annotations then we use as training fodder for the learning algorithms I'll talk about. Now we've been doing some work. In fact, there was a grad student of ours who was an intern here a couple of years ago, and actually last year as well, who did some work on sort of bootstrapping techniques for named entity extraction, and we're exploring those techniques further. And I'm not going to talk about those. I think I still bootstrapping techniques that try to infer, so do things like this. Oh, I know these are names of genes, so let me look in the text where those names occur and see what the context in which they occur. Can I extract some features from that I can use to learn a better extractor? That kind of thing is a kind of an idea that many people have pursued over the last 10 or 15 years. I think the jury is still out how well it works. I mean, I certainly for this task doesn't work well enough yet. There's too much junk is brought in, and we don't quite. So we have a new paper in submission that moves the ball a little bit forward, but I'm not convinced technically that what we're doing is right. I think there's something we're missing in that space still. That's what we like to do because labeling data is a pain, right? And also it's difficult to get high quality annotated data. Is that any other questions at this point? So this is one motivating application, and I mentioned the gene prediction as the obvious important task, which is so the main challenges in building these structures, assigning, is that there are a bunch of decisions you're going to make. So I use this kind of toy example where to elucidate the question, which is, if I am trying to analyze this sequence and try to say, well, what goes together with what? Well, is it a show about fake news or is it a new show that is fake? Well, there are two decisions to make. You're making two decisions and they interact. So if I decide to put this together, now I'm forced that way. Whereas if I decide to put this together, I'm forced that way. So those interactions, now how do I decide, make this decision, right? And many of you who have worked in natural language processing know that you like to exploit a wide variety of features of the text. And the general picture is if I can use those features and I can have some inference mechanism that given those features, tries to evaluate possible analysis and decide which one is the best. Now that can be costly because in general there might be a very large number of analyses for a given sequence, typically exponential length of the sequence. So this is all kind of basic stuff. So this general setting, and now we're going to get a little bit more technical for a while, again, not very technical, that I'm going to talk about is the notion that I have sequences, so I have sequences with some alphabet. No, bold X is always going to be an input sequence that you're going to try to analyze. And that's been, for text, it might be a character sequence, or it might be just pre-tokenized by some method. I use bold Y to represent possible analysis of a sequence. Now, I am not going to, for much of the discussion, it doesn't matter too much of what that is, but there are some constraints on what it has to be. And then what I want is to say, well, I have a way of scoring these pairs of an X and a Y. I'm going to say, well, given an X and some parameters that I'm going to learn, I'm going to find the best Y, that is the Y that satisfies some optimality criterion according, which is parameterized by those parameters for a given X. And so that's the task that we normally do. Now, people who have worked, say, things with hidden Markov models are very familiar with this. Just as one quick point, I'm just going to, again, for terminology, a lot of the time, the analyses are going to be done in the following way. Ignore this here. Which is, I have the input sequence. I'm going to assign to each of these input tokens a label, corresponding label, that tells you what the role of that token is in the analysis. So that's sort of just, again, terminology notation. So this very often, that's how we do this when represents this. So there are basically two approaches that people have used before the work I'm going to talk about, which is work actually been going on for 7 years, so it's not really new. But there were two general approaches that people used. One is generative methods, and that basically think about this pairing of an x and y as a stochastic process of some kind, which is parameterized. So here's my making up, generating a structure in the corresponding text. So I'm generating x and y together through some stochastic process. And my decoding is going to be, I have a probabilistic model of that stochastic process, those pairs x, y. I have the parameters. I'm going to find the y that maximizes that joint probability for the x that I'm interested in, and that's what I get. That is a standard story that you people do with hidden Markov models or with the probabilistic context free grammars. Another technique that people have often used is, and I'm going to use here, is one way to say, well, I see the word fake. What do I do? Oh, I don't know. I'll just wait and see the next word. Oh, I still don't know what to do. I could either put those two together or not, so I'll decide not to put them together. See the next word, and I say, oh, what do I do? Well, I have two choices. No, not really. It is the end. Suppose I have an end marker. So I say, well, there's the only thing I can do. I put those two together, and now put those two together. So this basically what you're doing is you're making one decision at a time, and you're going to you have to decide whether to wait for the next word, which is shift in a shift reduce parser, or reduce, put them together. So you have a classification problem. Just decide shift or reduce at each point. And you learn a classifier. So basically what you want is a classifier C that, given the input sequence, maybe you can look ahead, and the decisions you've made before is going to give you the next decision. So these are the two ways that people have done until basically 2001. Basically, these are the two ways people did this type of problems, as far as I can see. And they were fairly successful, but both types of approaches have difficulties. Now, some of you have heard this story before, and by now it's kind of digesting your lunch. But since I don't have a complete model of the audience, I'm just going to remind you of this. The generative story, like hidden Markov models, probabilistic grammars, requires a complete representation in terms of this stochastic process model of the input-output relation. And that makes it very hard, and this is a technical point in the theory of graphical models, to model non-independent features of the input that arise here. So if I'm doing text, for instance, information extraction, features like the word ends in ing, the word is capitalized, the word appears in the dictionary of common first names in the United States. All of these features are correlated. So maybe capitalized, appear in the dictionary first name are positively correlated, ends in ing is negatively correlated with the others. However, if you want to capture those correlations precisely in your probabilistic model, you produce a very complicated graphical model that's very hard to do inference with or do learning with. So so this is a very nice, clean, probabilistically motivated approach, but it suffers from this difficulty. Now, there are ways around, or attempts to go around. For instance, you can use sampling techniques rather than using the exact inference and many other things that people have tried. But for very large-scale problems, for instance, certainly the problems like gene prediction, becomes a very, very challenging thing to deal with. The sequential approach doesn't have this problem because I don't have to model the input. I only just look at the input and say, what do I do given what I've done before and the input? What do I do next? So I can exploit a variety of features of the input, and I don't have to worry about which features to use. But the problem is that the way it's trained, you're training to optimize this local criteria and say, do I get the right decision at each point? And that can basically move the push the learning down the garden path where you are blind to the future decisions. So I can make a decision that's good locally, but pushes me into a dead end globally. And this is something that Andrew McCallum, John Lafferty, and I call label bias problem in the paper that we wrote in 2001 that introduced these ideas. So that's kind of the setting. So this is where things were roughly 7 years ago, as far as my story is. Now, other people might have different views of the world, but as far as I can see, that's basically the two options we had if I was doing information extraction or gene prediction. So, for instance, you take about all the gene predictors in existence, actually, that are widely used. They're all hidden Markov model-based, with some tweaks, some hacks here and there, but essentially hidden Markov model-based with very poor ability to model local correlations in the input features. The best text information extraction tools developed, for instance, the work at BBN, was also hidden Markov model-based. And that was basically the state of the art for these problems around 2001 or so. Now, what we've been doing since, and this is work that, as I said, Andrew McCallum and John Lafferty and I initially did, and they have, Andrew has continued to do a lot of work along these lines in various ways, and I've gone into a slightly different direction technically, but essentially with the similar goals, and looking at different problems than he has, I like to retrospectively think of it, although at the time I didn't think of it that way, as a simple generalized, and this is actually, the way of thinking of it this way is a kind of owes a lot to Yoram back there, this student, Kobe Kramer, who's now a postdoc with me, the idea of generalizing linear classification. So this builds on a paper of theirs, which is a work on multi-class support vector machines and other ideas around that. So basically what we're going to do is to say, well, I have x's and y's, and I'm going to have a bunch of features of these pairs. As features are observations. Look at the x and y. Are these a good pairing of an input x and output y or not? And you can have, so you have this big F here is a feature vector. It's going to say, oh, I like that, I dislike that, I may be like, so basically you might think of it as binary, not necessarily, it need not be, it might be a real value, but mostly for applications we write, that's a binary feature vector that says whether I like, or there's good agreement between what the input looks like and what the output, the proposed output looks like. And each of those features gets a weight. And then finding this particular, finding the output y, sort of the proposed output y hat is maximizing over this. Now, of course, as many of you will notice immediately, that is not, that's not tractable in general because there are exponentially many y's. So what we're going to do is that we're going to do exactly the same thing that people do for HMMs and probabilistic context programmers, which is to impose some kind of a Markov assumption in this inference problem. So what we're going to do is think about this feature function as a sum of feature functions that look basically can look at all of the input x, but only a little piece of y. So a bounded piece of the output structure y. So these f sub c's, we call these local domains C, is going to be a function just does depend on a subset of the choices that you can have for y. So for instance, if I'll give you, I have a picture here. Why don't I show the pictures? So here's an example where we're doing something part-to-speech tagging, which is another task where you assign to each word it's most likely in context part-to-speech. So this is JJ is sort of a brown corpus label for an adjective and used for a kind of noun and show for another noun. And the local domains might say, well, I'm going to look at consecutive pairs of labels. And consecutive pairs of inputs. But I could also, for instance, say, oh, consecutive pairs of labels, and I'll also look at that word, that word, that word, and that word. The input, how I look at the input is completely immaterial from the point of view of the combinatorics. How many labels I can consider at a time is critical, because what you want, and this is a very general idea comes out of the theory of graphical models, is you want to, so here's a case where I would do the same kind of thing for trees. Again, you want to have these local domains. And what you want is a way where these structures decompose in a nice way so you can do dynamic programming. So it's essentially what makes hidden Markov models work well. So if you have these types of tree structure interactions, so if you talk to the graph involving these local domains and their overlaps, this graph forms a tree and you can do efficient inference. And this is well known. And so the only point here is that although this was developed for graphical models in general, you can think of it independently of a probabilistic interpretation, and simply with respect to solving the inference problem, which compute this max in this particular objective function. So now, given that, I want to learn one of these things. So I'm going to, I came up with some local domains for my task, and it's like my head or my students' heads most of the time, which is say, well, we want a model that looks at, say, the last label, and so the two labels, consecutive labels, or maybe 3 consecutive labels, and engineer some feature functions that correspond to kind of what's important about the problem. And now we're going to do is to adjust W to approximately optimize some objective function on some training data. And there are many ways of setting this up. And again, Yoram Singer back there knows a lot more about this than I do. But the general picture here is that I want to minimize some loss. So I have some training pairs, xi, yi. These are truth, or at least as much of truth as I can get to. And I can compute, given the pair xi and yi in the current weight vector W, a loss. How much did I goof in trying to label xi? I will produce some y which doesn't agree with yi, so I'll pay a price. I compute a loss over all training instances indexed here by I, and then I want to have some means of saying I don't want all W weight vectors equally, because if you allow W to vary without any constraint, I could overfit the training data very badly. So I could decide that what I want is to take the norm as weight vector and keep it small. And you have some penalty term for that. You can do other things. You can, instead of having the L2 norm, you can have the L1 norm. You can do a variety of other things along those lines. Now, some of you, I'm sure, have heard of this notion, of this idea that is, in fact, what our original paper with John and Andrew was about, is this thing called a conditional random field. And there's a particular instance of this where the objective function has this loss function here. I reproduced that equation there. Is essentially minus log likelihood, according to a sort of a log linear model, a Maxent model. Basically, this is the minus log of the probability of y given x, where the probability of y given x, is just basically is the e to this minus divided by some normalization, and I just took logs out of all that, and this is sort of a normalization to make sure that these are proper conditional probabilities. So this was a CRF model. I'm just recasting it in this general way. So this is what we had in mind. It's just we had a conditional probabilistic model. It's a generalization of the Maxent model to the problem of sequence labeling. And then later on, as part influenced again by Yoram and Kobe, I started thinking that I wanted to decompose the problem of describing the problem and what optimization I do. So this is a pretty good optimization to do, but not necessarily the only one you might want to try. Now, for all the applications, and for a reason which I'm about to describe, so just to be the most technical and it's not very technical part of this. I'm going to use some again, it's about notation. I'm going to say what we're going to look in the training algorithms that we're going to use is this notion of a margin, which comes out of the theory of sports vector machines and the sort of statistical learning theory. So I have an X and two candidate Y's, Y and candidate structures Y and Y prime, and I'm going to compute the advantage, the score advantage of Y over Y prime. This is the margin between the two of them. So how much do I prefer Y to Y prime, basically, what that quantity says. And then given that margin, I can, the original, so the CRF loss can be rewritten this way, up to some constant that doesn't matter. So basically, this is the log loss, which is maximizes the probability of correct output, which is CRF does. But often what I'm interested in, maximize probability of the correct output, is often not what I want, because that's not what I measured on. I measure not on probability. I measured on how well do I label things. So let's try to optimize that directly, or at least as close as we can. So for instance, I could say there's given to a Y and a Y prime, there's some distance between them. And for instance, it could be the Hamming distance between the two sequences. And I want is to minimize this misclassification. So if say Y is, if this distance is huge and Y is not preferred by at least as much over Y prime by at least as much as that distance, I should pay some price. I want to say, I want my score to overwhelm the gap. So if Y is much better than Y prime in terms of the distance, say the Hamming distance, then I want the margin to be, the margin of Y over Y prime to be at least that big. Otherwise, if it is not, I want to pay a price. So the general idea here is I want to keep things apart by as much as at least as much as the sort of the Hamming distance between them. Yes?
This might be a question for the experts, and we might take it offline. But you mentioned that you're not interested in probabilities.
Yeah.
But
not necessarily. Not necessarily. Not for these tasks.
But if the way you define it, if this is a decision problem, you're not really interested in minimizing the error. You actually say, if I sort of predict a sequence whose Hamming distance is too far from the correct sequence, I'm actually being penalized much more. Because the margin actually, so you define your loss to be the Hamming distance minus the projection.
Yeah.
So sequences, so if your prediction is pretty close in Hamming distance to the correct sequence, you're actually being penalized less. And now the question is, what is the decision model that stands behind the,
That I don't know. I mean, that's the kind of thing you do, not the kind of thing I do. So actually, let me just say that for the applications I'm going to talk about, I don't use the Hamming distance. And now, there is no theoretical decision model behind these. These are empirically chosen losses that worked well for the applications. So I'm going to be completely an engineer with respect to this. Now, and I left my theoretical friends try to come up with a decision theoretic explanation for it.
My explanation is very technical. Most of the methods, not yours, sort of use actually dual approaches. If you go to the dual, the Hamming distance decomposes over the sequence, and you get a very compact dual form. If you use just the 0-1 error, say is the correct sequence or not, there is no simple decomposition, and you can solve it in the dual.
Okay, so this is the paper that you sent me that I haven't read yet. so I had actually to give I had to prepare the talk, and so I didn't have time to read the paper. In fact, these are the two losses. So 0-1 error, that's what you talked about. It's versus using the Hamming error in these two examples.
Can I ask a question from New York here? Sorry.
Yeah, the New York.
Yes, about your previous slide and viewing this by working the loss function into the objective function and viewing this as a classification problem. It seems like in some ways it would be natural to view this as a regression problem. Can you just comment on that?
This as a regression problem.
Because you're trying to predict the structure, right?
Yeah.
So Can this be viewed as a regression framework where the value that you're trying to predict is the output label y, or the output structure y?
Well, when you say, I mean, so what I don't quite understand is when you say regression. I mean, there is a sort of a step here beyond. So you could imagine that computing the score is a regression. In fact, it's analogous to computing the exponent in logistic regression. The problem is that then there's a combinatorial optimization problem, which is to find the best discrete structure y, the discrete structure y with the maximum score. So, okay, so in the case of classification, this is trivial. Finding because you have a small finite set of labels, or maybe in this case of logistic regression, just two. So finding the best label, the best scoring label is trivial. So you can say that the score part is doing a linear regression. The point is that then I have this combinatorial optimization problem to solve in addition. Does that answer the question?
But doesn't that occur in the classification setting also?
Well, but the optimization problem is trivial. The inference problem, the part of choosing the best scoring label is a trivial, that's a trivial problem because you just have a small finite number of labels, you choose the one that has the highest score. So that's bounded, that's a kind of a constant factor, whereas in here the number of possible y's is exponential on the length of the input. Okay? So that's the difference.
I think there's another answer. So you can look at the log loss. If you look at the binary classification problem, then the log loss is exactly the same as logistic regression. Mm-hmm. And if you turn that around, then you can look at the log loss with multi-class classification as a generalization of logistic regression.
Mm-hmm. Yeah.
And all the other loss functions you're introducing are then generalizations of the log loss by introducing this distance function, which you can tune according to your application, mm-hmm. like F-score or blue score, yeah. or whatever scores you're looking
mm-hmm.
at.
Right. Yeah.
And I also had, I wanted to comment on your history yeah. of the model. So you said first there were the generative models, then there were the sequential models.
Well, yes, first they were concurrent, right?
Yeah, but I just wanted to point out that the log loss models, so the discriminative, conditional, log linear probability models, they have been around before the CRFs came along.
Right, for particular applications. I mean, so they were, I mean, the main one, I mean, being parsing. I mean, so there was a sort of a...
I think that the real innovation is that people introduce this, this new parameter of the loss function of the distance function into the loss function.
So I think there are several. I mean, I'm not to say. Who am I to say what was the real innovation? I think that there's a package of things here. It's very often the ideas in the package in some package like this. The ideas have been around in some form or another. What we ended up doing, you know, and I was not saying a kind of very enlightened and sort of a, you know, sort of knowing everything in advance is by kind of we stumbled over time into breaking the problem into modularizing the problem into different parts and seeing that actually, so for instance, these log linear models for problems with a very large number of labels, for instance, parse trees or whatever. So people always thought about that, you know, everything was presented, okay, these are sort of a generalization of Maxent models. And then you can actually decompose that into two things. There's a linear model, which kind of gives a scoring function. And what's important about that linear model is whether you can, you know, what the computational problem doing inference in it. So that's, so inference in that log linear model, which is one set of issues, so the log linear model or the sort of linear model, and doing inference, which is find the highest scoring structure for that, and then what you penalize, what objective function you use for learning. So it's essentially it was going to do surgery on what people are already doing, and say that there are these different degrees of freedom you have that maybe were not obvious before. Or at least certainly wasn't obvious to me. Might be it was obvious to other people, but certainly not to me.
I'm just saying, as soon as you generalize your loss function to incorporate something like F-score or blue score
yeah.
or whatever, what other actual function you are interested in for your application, then all the things you did before in the probabilistic model or in the general, you can lose all of that. All your dynamic programming stuff, it may all go wrong and it doesn't work anymore. And so that's really, you have to start from scratch once you look at those kind of models.
Yes. I'll let me just move on so to stay on time here. So what we ended up doing, and this is again based on a work that exploiting the work of that Kobe did for his dissertation, is we meaning now what we do in my group is sort of the way I approach these problems in the practical. It's been move away from global optimization of the kind we talked about, for instance, in the log linear models, and move to online training methods where you process one training instance at a time, which and they're nice because here's roughly the learning algorithm, right? Although of course there's some things in blue and red there that are subroutines, but you basically have a set of training instances numbered 1 to n, and for a number of epochs, I start with the weight vector, which is 0, and for a number of epochs, I'm going to classify an xi incurring some loss L, and then update W in some way, appropriate way to reduce L. And the technique that we use for the results I'll describe in a minute is again based on the work that Yoram and Kobe did. Is this idea, and he'll forgive me that I'll describe it this way, but that's the way I like to talk about it. And there's a lot of theory behind this that they are much more qualified to talk about than I am. So basically, you have the weight vector, and what you want to do is, for each training instance, you want to do is to project the current weight vector onto the subspace defined by a set of constraints that say the correct labeling should be above the incorrect candidates by an amount that is proportional to the distance between them, whatever that distance is. So, for instance, might be the Hamming distance. So, in a kind of formally, I'm going to find the way to think about this is you find the smallest update to my weight vector. So I move from W to W prime. So I'm going to find the smallest update here that allows me to have that all the y's, for any y, yi outscores y, that's the margin, by at least as much as yi is better than y. So so now the problem here is that and this is what Stefan was alluding to. I'm counting over all possible y's here. And I, in general, cannot do that. So now, for the particular case where this is the Hamming loss, you can do some special things because the Hamming distance decomposes in an appropriate way. There's something called, you can do this thing called loss augmented max, which is a technique that, for instance, Ben Tasker used for his max margin, sort of the max margin Markov network work that he did for his thesis at Stanford. But in general, if this is not decomposable in a nice way, and this is at that point, then this is not possible. So we cheat. I don't have any false humility about cheating in these things. I just say, since I exponential many y's, let's select the k highest scoring ones, where k is a small number, and very often k is 1. Sometimes for some applications k has been like things like 5, but for the 2 applications I'm going to talk about, k1 works as well as anything. So I just basically take the correct labeling and the one that my current model produces, and I say, oh, the one that my current model produces, which is the best scoring one, has a score that's higher than the correct one. I don't like that, so I'm going to change W, the minimum amount, to correct that, to make the score advantage to the correct one be as much as the distance between them. So if my current model is very wrong, then I'm going to change W a lot. If my current model is not very wrong, I'm going to change W just a little bit. So it's kind of it's like perceptron with perceptron algorithm with a variable learning rate, which have to do how bad am I doing? Badly am I doing? So all of you, or most of all of you, this is a slide that's here because I'm using these abbreviations on the results I'm about to kind of overview. So true positives, true negatives, false positives, let's have a specificity or precision, sensitivity, recall. By the way, I don't know whether you know this, but computational biologists are evil because these terms, specificity and sensitivity, are in biostatistics used in a different sense. But they decided unilaterally, computational biologists, to call specificity, what they call specificity, what we call precision, what they call sensitivity, what they call recall. Whereas biostatisticians, actually, what they call one of these, I can never remember which, is not, it's some other combination of true, false, and so on than this one. This has just confused me to no end for a couple of years until I just kind of figured out that, oh, okay, they mean precision and recall. So we are happy. But because we are publishing some of the results in biojournals, we have to talk specificity and sensitivity. Even though, of course, that confuses the biostatisticians who think of sensitivity and specificity meaning something else. And often we want to combine these two quantities, and we use a harmonic mean of the two called the F1 measure, which for you who do IR and so on are well known. So I'm going to just quickly go over the two applications that we've worked on. One is, and they have some kind of interesting things to illustrate with both of them. One is for text. So in text, we use a wide variety of features, things like label configurations and various properties of the input, such as the identity of terms, membership in term lists, various orthographic patterns, things like regular expressions to say, oh, this is a token made of digits only, or start a capital letter with capital letters followed by some digits, which is very useful, for instance, for gene code, names that are some ABC1, ABC5. Common prefixes and suffixes in the, you just throw in everything that you think you're going to need to the extent of the memory you have, and then conjunctions of those to some extent. So this is the main engineering task. Now, it is not a huge one. For this text, for the protein stuff, Ryan did the first version of this, and it probably took him 2 weeks to do the feature engineering. And then Kuzman Genchev, was another student of mine, did another 2 weeks of work on that. So doing a little bit of feature engineering again. And the results I'm going to talk about is the result of his 2 weeks on top of Ryan's 2 weeks. So it's total 4 weeks of graduate student time in designing the features we've used.
On your remark about using first top K,
yeah,
and that, when you do that approximation, so what do you do about weighting these K items?
We don't.
You treat them equally.
Yeah, but as I told you, most of the time we just use top one.
Right.
Remember, they are weighted implicitly because they are weighted by their distance. Right. So they're not all at the same distance of the correct one.
Because you use distance to decide the correct. Or
no.
You use
so basically, there's implicit weight the ones that in the constraint, if the third of those is very, very far. So this leads to an issue, which maybe what Yoram also referring to. If I have one of those top K, which is enormously far in Hamming distance from the correct one, say, suppose I'm using Hamming distance, it's going to have a huge influence in my update. But that guy might have been a candidate that I would never want to consider anyway. So it's going to do a big update to my weight vector and distract me. So I think part of the reason, actually, we are doing this top K typically doesn't help much is that the competitors that appear in this top K, if K is big enough, are just total junk.
So maybe I'm not understanding it right, but it seems like also if you do top K, you're always guaranteed that there is a solution, or top 1, that there always is a solution that satisfies your conditions. But if you have K higher than 1, it's not, and you have a linear model, it's not necessarily guaranteed that you can actually satisfy all of your conditions at the margin.
Well, remember, it's greater or equal, right? So you're telling me that it could be unfeasible? Let's see how. Because they are not equalities, right?
Right, but you don't have Slack for, you don't allow for.
Oh, Slacks. Yeah. Well, okay. So you're good. We should use Slacks, but we don't because in fact, it doesn't matter. For these applications, we've we have a solver that uses Slack variables, and doesn't help. So, yeah, you could. We have that solver, but it's in practice, it never plays a role. These things because we use so many features that these things are really approximately separable. That's the reality. If you throw enough features of anything, you can separate it. That's basically the default theorem, right? Yeah. Actually, I'll tell you, there's a caveat on that, on the gene prediction, I'll tell you.
So you're kind of implying that if you increase k, your actual empirical error rate could go up.
Actually, I've seen that.
So that means that maybe that underlying theoretical model is not actually very useful, and this is going back to what Stefan's saying. Maybe you should start from the beginning and say, well, I'm doing a generalization of the perceptron, and I just have some function of f and x and f of x and y prime, and I'm just fiddling with that function. The other stuff is just...
What other stuff? I'm not sure what you...
Well, I mean, like, you're talking about the margin having to sum over all the margin, you know. So in terms of summing over all possible y's...
Oh, right. No, so...
That's not really, I mean...
But, right. No, I agree with you. I think. And Joran might have a different view on that.
I have sort of a very theoretical explanation.
Yeah.
Which is, what happens is that the perceptron is actually not these are not generalization of the perceptron, but the perceptron is a special case of these updates when you work on the vertices. Right. But unfortunately, if you look at the theorems, all the algorithms achieve the same mistake bound that the perceptron achieved. Mm-hmm. And why is that? Because in the case where each example is completely orthogonal to any of the previous examples, all of the updates actually, all of the different settings give you exactly the same update. There is a complete innovation in the new example. And in these sort of very high dimensional spaces, it's not that all the examples are orthogonal. Each example is give you completely new information, but they're roughly, they're very small similarity, at least at the beginning of the learning.
You have enough features.
Yeah. So in fact, you can see that if you're learning with perceptron, there's not a huge difference in using perceptron or using mirror to start with, sort of the beginning of learning. But then later on, you start getting some difference. When you get relatively few errors is when it really matters.
What are the theoretical properties of your modified perceptron learning rule? Do you guarantee convergence in the same sense that the perceptron learning?
Which modified rule?
The update step where the perceptron learning rule takes a small step and you take a big step.
Yeah. So that's those theorems are in the Kobe's dissertation, and I guess in the paper that you guys have in JMLR in 2006, right? So I delegate that to those guys. I'm the hacker here. So, but basically they are similar convergent. I mean, they're slightly different. I mean, so if Joram, correct me if I'm wrong, but there's slight differences. I mean, in some of the results with respect to convergence rate, but they are pretty similar to the perceptron ones.
So if you're just interested in the number of mistakes, the result is identical. What these algorithms give you in addition is, suppose you also want to count the number of times you were inconfident in your prediction.
Yeah.
And you get a more general value.
Yeah.
Okay.
So just to kind of wrap up on the results, I don't want to go too much over time here. So I just wanted to give an example. That's kind of a nice point that I want to make about using different losses in training. So this is identifying gene protein mentions in PubMed. This is a test that was done. This BioCreative 2 competition just finished a few months ago. And this is one of the best, not the best result that people, I don't know actually, we don't know yet who got the best number, which is like around 88 here. This is this is a result of doing some additional feature engineering and using this different learning algorithm. So log loss basically is using a CRF learner. And this is using that algorithm using where I'm taking number of false positives with twice number of false negatives as my loss function. And it's interesting that this is actually a very significant gap in Ryan's original set of features. We threw away a few that seemed not to help. Then we added some clustering information, did unsupervised clustering of words, and used those clusters as additional features. This is based on an idea by Scott Miller that Gideon Mann at UMass implemented for this task, and that helps a little bit. And then dictionaries, which of course, can help substantially, although they don't help much here, help a little bit here. So in fact, you see the gaps between these things vary depending on which log loss you are, which loss you're optimizing. So kind of the take-home message on this is there's a sort of subtle and not obvious interactions between the choice of loss and how features contribute or not contribute to your quality of your results. So there's a sort of a piece of engineering here in this table. This is what Kuzman did. The feature part and figuring out different losses when we were doing these biocreative things.
So are these numbers F1 or what?
Yeah, these are F1 numbers. I'm sorry. Yeah. So 86. So this actually in practice, these numbers are actually pretty good. The system that that system I showed, Fable, using an earlier version, actually Ryan's version, which is more like 82 something, and on a slightly easier task.
Since you're interested in F1, why don't you optimize F1?
Turns out, for reasons that are a bit complicated, which have to do with how this is being evaluated, which is not exactly by F1. They are measuring F1 in the competition, but they're evaluating in a funny way because there's a gold standard and a silver standard for each gene. So you're actually competing not necessarily against the correct one. There's a sort of a subtlety in how they are measuring quality. And this F1 is a convenient number to give here, but in fact, when you did on the development data, this is worked better than just optimizing F1, a little bit better. I don't have that number here.
But if you have the exact way they measure their performance, why don't you optimize that?
Well, it wasn't so clear exactly how they were going to measure it. That's the problem. These competitions, remember, if you ever run a competition like this, or Ryan over there has run a competition recently, you know that there's all sorts of little dark corners in deciding how you evaluate it. You decide that your evaluation metric after it's maybe not the right one. So I cannot be optimizing their evaluation metric because it's not totally clear what it's going to be. So I have to come up with something that's sort of reasonable in the ballpark because they will change some aspects because people say, oh, if you do that, then there's this counterintuitive result. For instance, people can cheat in this way. Right? I mean, there's a debate going on all the time as the competition goes about these things. People come out with the issues and so on. So you cannot really track that exactly.
So how sensitive is this to that 2 factor in the false positive and 2? I mean, if you just had false positive plus false negative.
It's probably not significantly different. I don't remember that. Kuzman just say, well, this is what I got that is on the development data that seems to work well. He tried, how many, did they try 15 or, I don't remember that. Yeah.
So, I mean, at kind of a level removed from all this, don't you sort of find it disturbing that adding all these features and stuff actually made less of a difference than just changing the loss function to something which is different than what the competition was measuring anyway, right? That made a much bigger difference in terms of the numbers than all the other engineering that went into it?
Yes. That could be a comment on competitions, actually. The reasons to do competitions for you are an academic. Well, there are people here who do competitions, so they have I'm sure they have their explanation. So it's actually that allows you to measure a little bit what you're doing against what other people are doing, and also forces. You've been a graduate student. You know that you sometimes have to force people to actually try something practical rather than writing papers. Let me tell you of another competition, and actually this is a more important one. So gene prediction. This is a very challenging problem. And I just want to wrap up because people have to go places. But this is actually the best results, the thing I'm most excited about. Gene structure is quite complicated. We represent the possible structures as a complicated finite state machine that has to do with the structure of introns, exons. There's some biological constraints that go into this finite state machine. I won't describe this. There's a paper in PLOS Computational Biology in March 16th that describes this in detail. There are lots of features that we use, things like statistics of protein coding, DNA, individual codons and dicodons as individual features. The length of the exon states is very important. The length distribution, the empirical length distribution is very important. So you have use some a sort of a non-parametric representation of length distribution. And very many patterns, motifs, and motif conjunctions that have to do with the structure of the DNA around the places where you change between introns and exons, and also the beginning of the exons and the end. It's very important biological, important but poor, not fully conserved biological evidence around there. So that's the point. None of these things are fully conserved by evolution, so there's a lot of variability. But there's also some patterns that are often informative. So this is a very large number of features. The loss function, again, is one of those things. Why did I use a loss function? Well, I didn't use it, actually. Axel came up with this. This is a loss function that's often used in the literature. This is base correlation coefficient. That's what he used to optimize which is actually, you could have used F1. It wouldn't be too different, but that's what he used in the just to give you an idea of data sets here. There's a nice thing. So the training set is a very large number of genes, human genes mostly, but not only, exons assembled from various sources. And notice that most of the DNA is non-coding. So this is actually a hard problem. You only to identify a relatively small number of useful information out of this big, extremely varied data set. 54 megabases in length. And then these are 3 test sets. The most interesting one is ENCODE. ENCODE is a very recently annotated, very carefully curated set of human genes. This is a lot of work has been done to make sure that this is very biologically verified. So this is the most accurate, to our knowledge, the most accurate human test set gene in existence. There's all the good ones for C. elegans and the Arabidopsis, which is a plant, watercress basically. But this is the highest quality that the sort of genomics community can put together. Even lower density of coding material. It's fairly large compared, larger than the other two. And this long table, which comes out of the paper, these are GenScan, GenZilla. These are 4 major previous gene predictors, all HMM-based, all with lots of tweaks in engineering. This is basically Augustus is the state of the art as of before we published this. Let me show you something which is really striking. Gene prediction accuracy. So how do I measure sensitivity and specificity? This is exact match. Did I find the gene exactly? And this is quite important for biological reasons I'll tell you later, if I have time, or if you can ask me. Even for human, which is the most studied genome, this is the numbers I get. These are percentages. This is terrible. And you notice that if you just look at exons, all exons, just over 50, you find correctly only over 50% of the exons that are there. This is appalling. How can they do anything with this stuff? So there's a huge amount of headroom here. So we move substantially better in just about everything. I marked in red the significantly better things. It's still terrible, right? Our results are still terrible. Like 13% for, 26% for genes, 23% for, 24% specificity for genes. But we move substantially over everything. And the only reason why we could do that is there are 2 reasons, actually. One is that we can exploit many more features than everybody else does and optimize them together. Second one, we can play with the loss function. And that was very important. And the third one is the learning algorithm. So here's an interesting point. We actually spent a lot of time, before we moved to Mira, we were using Perceptron, because based on Collins. And before that, even we are trying to use maximum conditional likelihood. And we wouldn't get anywhere. These things would just fail miserably, overfit horribly the training data. There were all sorts of bad behavior. And the reason is this data is extremely complex. And you have not a very large number of training instances, but each of them is a long, complicated thing. And, empirically, and I don't understand this fully theoretically, mirror is a much more robust method in a situation like that. Perceptron failed completely because the problem is highly non-separable. And mirror, even without slack variables, still can handle that pretty well. Whereas the perceptron algorithm totally flailed and oscillated. It never got anywhere. Or at least sometimes it would, but you have to play with learning rate, be very careful, and then you work on one test set and not another one. Mirror is the only one that we have confidence that it will work across different species. In fact, we applied this to C. elegans. We had never worked with C. elegans. Axel, over the Christmas break, instead of going away on vacation, entered the competition for NGAS, which is the nematode gene prediction competition. And we don't know what the ranking is yet, but certainly his results were better than any of the gene predictors they could get his hands on. And we had never worked on C. elegans. We didn't do any engineering for C. elegans. It's a nice picture, which is actually in the cover of our article to show you the annotation, the quality of our annotations in a bunch of examples. So this is the standard annotation. This is our prediction for some examples. And then I, of course, have made mistakes as well. But compared with everything else, for the most part, we do way better. And that shows. By the way, finding the first exon is especially important for lots of applications. And we do quite a bit better for first exon than anybody else. Actually, that's our biggest advantage. Just wrap up. Training data is a pain for the supervised methods. None of us likes to annotate data. In fact, annotating data is very hard. For the genomic case, building these annotations is extremely expensive, high quality data. So we've been working on a couple of different things, which I won't have time to talk about, but I can talk one-on-one with you later. One is this idea of unsupervised adaptation from one domain to another. We do this for part-of-speech tagging between Newswire or sort of Wall Street Journal and biomedical text, and got some nice results. This is a way of essentially finding correspondence between features in the two domains for a linear model. This is work of John Blitzer, who some of you know, actually the part-of-speech tagging was also done with Ryan, and we've done other applications of that since then. And then we've been working on those bootstrapping techniques that I mentioned already before. This is Partha Talukdar, who also was an intern here before for a couple of times. Actually, at this point, what I'm most excited about is possibly applying these bootstrapping techniques for gene prediction. There's you can exploit evolution to help you, because you can use comparison to other species for highly conserved genes to give you some guesses, initial guesses of where genes are, which are pretty reliable for a small set, and use that as to bootstrap the gene predictor. This is a new project which is starting. So using annotating unlabeled data from other sources and trying to use that as seed data for learning is certainly something a lot of people are doing. I don't know whether I have any really good ideas for this, but it's certainly something we're working on. Final thing we are working on is theory, which is, what if the inference problem is intractable? These two cases, the inference problem is intractable. I'm lying. In the gene prediction case, I cannot do full search. So we're doing beam search because of the semi-Markov property. We need to keep lengths, and you cannot, So what if inference is approximate? So we're using approximate inference because full inference is intractable. Can I learn? Can I learn properly? Turns out that you can have the teeny simple counterexamples that show that even a good approximation algorithm for inference can lead to total inability to learn. It's actually quite counterintuitive until you actually look at the example. So, but on the other hand, people do this all the time. For instance, some of the Ben Tasker's results for image segmentation, is using approximate inference. It does pretty good, even though it's not, it's using approximate inference. Why does it learn? We don't know. We have some ideas. We have made some progress, both negative and positive results, but we still don't know. I mean, we know better what we don't know. But it's this is a very important thing, because when you move these techniques for more complex combinatorial problems, for instance, in image segmentation or video segmentation, you would like to know whether by using an approximate inference method to do in the inner loop of learning, that you're getting somewhere rather than just going completely astray. And we don't know, we don't have any theoretical foundation to decide when are we doing something good, reasonable or unreasonable. So that's all. Sorry for the longer time, but hope it was still useful. Thank you.
So what distances did you use for the gene?
So this is this funny thing, correlation coefficient. Basically it tells you 1 minus correlation coefficient. You try to find the correlations between the decision, the single nucleotide decisions. Say you say, oh, is this nucleotide part of an intron, an exon, or not? So this is basically a four-way or a three-way decision really, and you're trying to decide whether that the correlation between those and the two labels. So that's that correlation coefficient. So if that's big, it's good. So 1 minus that is your loss function. And that's why we do that? We wanted something that's all combined precision and recall. And it's just Axel took that one out of the literature because he had had code for it and so on, and to measure it. So you say, well, I'll use this loss function, and it worked better than certainly much better than Hamming distance. In fact, that was another of the tricks that we needed. So I mean, part of this story is a story of a lot of detailed engineering over time, but also a set of recipes that I think are useful for if you are doing something like this, then I think there's a sort of building blocks here that can be used over and over again with modifications, but which you have a certain confidence, which not necessarily based on yet a lot of theory, unfortunately, but is certainly, I'm feeling much more confident today than I was 6 or 7 years ago or 10 years ago, that you can apply techniques like this where you try to optimize across a very large number of features for sequence problems and get systematically pretty good results. Maybe not the best results. You could always engineer a solution for a particular problem that is better. But you have to say, in the case of the gene prediction, which is the most challenging thing I've ever done in this kind, because I didn't know anything about gene prediction to start with, besides kind of a Scientific American. And Axel did. He used to work at a conventional biology company for a number of years before he came to Penn. But the problem is that there was also a lot of mechanics to do with various issues with the data, the nature of the data, various issues with the nature of the annotation and mistakes in the annotation, but also issues with which learning algorithms would work. It was for a long time we were trying many different things. As I mentioned, perceptron and CRFs and so on. They were not really making progress. And there's a kind of a little kind of vignette side story here. So when we wrote this CRF paper, several other people thought, oh, CRFs, this is a good idea maybe for gene prediction. So there was a group at Stanford, and there's a group at Max Planck, and there was also someone at UMass, one of compile person there. And they all thought this, and I kind of felt, oh, gee, we're going to be scooped. These people know a lot more about this problem. They're going to. So we've been working on this for 4 years, basically, very quietly. Because, it's a small group, just me, who have a day job, and my student. And we had to deal with lots of difficulties along the way, but in terms of the total amount of effort, you can say it's like 4.5 years of effort for a new gene predictor, which is not a lot. Most of the other ones that are there are much, groups of 10 people working for 3 or 4 years, things like that. Not the original GenScan. GenScan is just basically one person and a half working for like a few years. But we basically beat them all to get, no one else has this kinds of results using these types of methods. And the main reason was because we're very cynical about the whole thing in the sense that we did not get too wedded to any theoretical model. So some people are saying, oh, we're going to do this with CRF training. So the guys here at Stanford. So they've been building more and more complicated CRF training stuff, trying to handle this large language problem, but not being able to scale because the optimization problem becomes really bad when you try to do global, trying to do something like, convex optimization with this very large amount of data. The guys at Max Planck are like support vector machine fanatics. They like the dual world. It has to be all dual. There's no way that you can, at least in the methods they were using, they could possibly scale to the whole problem again. Because when you move into the dual space, you have this, you have to compare everything with everything. And these sequences are very long. So you have to compare every piece here, everything, whether a piece there, in computing this sort of essentially doing this sort of kernel computations. You die. And that's what happened with them. They couldn't. In fact, they were talking about this at the NIPS workshop, and they were saying, William Noble, the kind of computational biologist at the University of Washington, saying, hey, when do you guys think, so they were working on C. elegans and only doing part of the problem, not the whole gene prediction problem. When do you people think that you could do this for a human? I said, oh, we couldn't possible because even training for this, it takes us 2 weeks to train just to find the splice sites, which for C. elegans, for human, we could never do it with these methods. Well, at that point, where we had our paper about to be accepted, it would take us a day to train this model, which on a normal computer. So basically, what we did was we really drove hard away from saying, okay, I want to understand everything from have a nice, completely clean theoretical model, but rather, I'm inspired by theoretical advances, but what we want is to have a real problem to solve. And what are the pieces, the building blocks we have in this collection of methods that are most appropriate? And often you find, you have some intuition, you will find empirically what works best. And so the basic, the thing that Stefan said was really an important point, which is by modularizing the loss out of the other things, you can start playing different games. Maybe in hindsight, maybe this is the most useful thing out of this line of work. But once you do that, you can start doing many different tasks with a certain expectation of relatively good quality. So not perfection. So, okay. Any questions?